Hi folks, welcome to GFG and Operating System Academic Series, and in this video today we are going to look into or continue rather with CPU scheduling. Remember, in the last video we have started CPU scheduling wherein we have discussed one of the natural CPU scheduling that is called first come first serve. So in continuation of that we are going to look into another important scheduling technique that is called shortest job first and also called shortest process next. Okay. And so shortest job first, essentially also known as, we generally write in short as SJF, and is also called shortest process next. We say SPN. Okay. Now, associated with every process, we will have a metric or a parameter selection criteria that is called burst time. So, this scheduling technique, the shortness of the process is based on the burst time of the process. It's not the size of the process, but rather burst time. I mean, at any point of time, when the processor CPU become idle, among the processes present in the ready queue, we are going to select that process which is having the least or shorter burst time. Process having the least burst time will get selected and scheduled onto CPU, dispatch onto CPU. And the mode of operation of this algorithm is non-preemptive, means the running program will not leave the CPU under duress, under force. It will leave the CPU voluntarily on its own like FCFS. That means it will run either till completion or perhaps when it needs to go for IO or maybe execute any system call, and then it will relinquish the control of CPU voluntarily. So here let me write the selection criteria. The selection criteria, the criteria based on which the process is selected from ready queue is burst time. And as I said, boys and girls, for every scheduling technique we have mode of operation which we either define as preemptive and non-preemptive. So essentially this is non-preemptive. Essentially this is non-preemptive. So let's read the points from the Galvin textbook slides. Associate with every process the length of its next CPU burst. Use these lengths to schedule the process with the shortest time. Next CPU burst means next time when it is going to, while it is waiting in the ready queue, the next time when it is going to run on CPU, what that is called the next CPU burst. So this burst time may not be the total burst time, the next CPU burst. And later on we will say why is it optimal, etc. And the preemptive version also we'll discuss at later point of time. Okay. So there are some challenges here, there are some issues here that we are going to cover. All these points are going to be covered. So, but before that, I am going to take a simple data set and then we will simulate the behavior of shortest job first in respect of this data set. So, in my earlier session, I made a mention that in case if there are no arrival times given, then essentially we assume all arrival times are 0. That means we assume that all processes have made entry at the same time. All right. So this is my data set. So let's analyze this data set. There are four processes P1 to P4. The next CPU burst time of the process is 6, P2 is 8, P3 is 7, P4 is 3. So among all these processes which are there in the ready queue, the one having the least burst time is 3, P4. So we are going to start at time 0, P4. P4 needs 3 units, so therefore non-preemptively it completes at time 3. Because there are no new process coming, so next lower burst time is P1. P1 needs 6 units, so 3 plus 6 it completes at time 9. Alright. And thereafter we are going to run P3. So P3 needs 7 units, so therefore it is going to finish at time 16, 9 plus 7. And finally we are going to take up P2, 8 units, 24. So if you want to calculate the average wait time, you can check that P1 has waited for 3 units. P2 has waited for 16 units, P3 has waited for 9 units, and P4 has waited for 0 units. So therefore, average waiting time will come out to be 19 plus 9, 28 by 4, and that is 7. So that is average waiting time. And of course, if you want, you can calculate average turnaround time. This is as far as a very simple data set is concerned. But for example, if I take some variable turnaround times. So I will take another example for your convenience. So please see, let's imagine this is a process ID and let's say this is our arrival time and this is the burst time. Say for example, I have the following processes and now the arrival times are slightly different. So this is 4, 3, 2 or maybe I will jumble it, 4, 1, 3, 2. All right. So this process has a burst time of 1 unit, this process has a burst time of 3 units, okay, and this has a burst time of 2 units, this has a burst time of 4 units, something like this. So how do we prepare the Gantt chart and show the schedule? So let's prepare the Gantt chart. So just in case when you are watching the video, my intention is you should basically pause the video and draw the Gantt chart and ascertain that you have understood the ideology. So this is the state of CPU at time 0. So boys and girls, if you observe here, there are no processes at time 0. So we are not going to start with any process at time 0, is it not? Time 0, the processor is bound to be idle for next arrival time. The next arrival time is at time 1. So boys and girls, don't think that we are going to start with P1, no. First, among the processes available, so at time 1 we have only P2. We have only P2, and since this is non-preemptive, so once I start P2, we are going to run till completion because it is not preemptive. So P2 starts at time 1 and need 3 units of time, so it completes at 4. It completes at 4. Is it not? Starting at 1, 3 units, so 4. Now by this time remaining all processes have made their entry. So who is having the least burst time? P1 is having the least burst time. So now P1 will take the charge completing at time 5. So followed by whom? Followed by P3. P3 needs 2 units of time, completes at time 7. And then eventually, finally, P4 takes the charge, needs 4 units. So therefore it completes at time 11. This is the schedule. And if you require, you can calculate average turnaround time and average waiting time. But essentially, I just wanted to tell you that the schedule length L will be nothing but 11 minus 1, 10. Maximum completion time minus minimum arrival time is the schedule length. In the schedule length, the idleness will not come. So please remember, this is shortest job first, also called shortest process next. Now, before we see the performance of this and its evaluation, we would look into what is called, let me just see whether we have the slides for SRTF or not, and then I will come to, shortest remaining time first. Okay. So essentially, as we said, shortest job first is supposed to be the optimal algorithm. So we say it is optimal algorithm. Why is it called optimal algorithm? Let's analyze here. So for that, I will write a small heading, performance of SJF. Or SPN. So as you see here, the essential characteristic of SJF is that it will always favor shorter process. It will always favor shorter process. At any point of time, among the processes present, always it is going to favor a shorter process. Suppose a process has come, a longer process have come in the ready queue and waiting and keep on getting shorter processes, then eventually what will happen to shorter process or longer process? Longer process will keep on waiting. So what I am trying to say, there are advantages and drawback of both favoring shorter and longer process. So let's analyze what is the advantage and drawback of favoring shorter process. So drawback is I hope easy to follow. The first inherent drawback would be starvation to longer processes. It will lead to starvation to longer process. This is the main drawback of shortest job first. But boys and girls, there is an advantage of favoring shorter process. So I hope you understand. The advantage is it is going to maximize the throughput. It is going to maximize throughput. Sir, how can you say it is going to maximize the throughput? Logic is very simple. Like for example, if you consider some duration of time, boys and girls, please have a look. If you consider some duration of time, like this duration of time, I say delta t. With the nature that we are going to always favor shorter processes, smaller burst time processes. So we are going to complete more and more number of jobs. In the duration t, because of the nature of shortest job first, we finish more number of jobs, we schedule more number of jobs. Throughput is directly related to the number of processes completed per unit time. That's why it maximizes throughput. Not only maximize throughput, it will also minimize the average turnaround time. Average turnaround time and average response time and also average waiting time. Because in duration of time, if I complete more processes, obviously the average turnaround time and average waiting time and response time will come down. Response time will not, right? We'll say waiting time. That would be more appropriate because response time and waiting time will be same for non-preemptive scheduling. Average turnaround time and waiting time. Fine. That's the advantage and drawback. But boys and girls, at the outset, before we take up the advantage or before we talk about the advantage and drawback, at the outset we say shortage job first has a practical limitation. It has a practical limitation. What is the limitation of shortage job first? The practical limitation is that how can we know the burst times? Burst times of the processes, next CPU burst time of the process are not known a priori. A priori means beforehand. Like what I am trying to say can be illustrated by means of a simple diagram. Like imagine, for example, this is my ready queue, and let's say this is the CPU. And at some point of time, let's imagine at some point of time t, I have received processes P1, P2, P3, P4. Now point is, who is going to run on CPU? That will be decided by shortage job first. These processes came just now. What is the concept of burst time? Burst time is the amount of time the process needs to run on CPU and complete its execution or leave the CPU, is it not? That is the philosophy of burst time. Now the essentially point is, when the process has not run on CPU, how do we know the burst times? The process came just now, P1 to P4. They have not run anything on the CPU. How do we know the burst time? So burst times will not be known. Burst times will be known only after the completion of the process or only after the process runs, execute on CPU and then leave the CPU. Then only the burst time will be known. Like the concept of the class lecture. I started the class maybe perhaps 15 minutes back. So what duration I completed, I know. But at what time I am going to finish my duration, neither you can tell or neither I can say. Neither you nor me. We can't say. The burst time, the real duration of the lecture, boys and girls, will be known only after the completion or the relinquishing of the CPU by the process. So burst times are not known, and obviously when burst times are not known, how do we implement shortage job first? So therefore we say practically shortage job first is non-implementable practically. Then question is, why do we have shortage job first when it is not practically implemented? There are two reasons for having shortage job first implementation. Number one, as theoretically we have proved, it is the ideal algorithm, optimal algorithm. Because of this advantage, we say shortage job first is optimal. Since it is optimal algorithm, it is used as a benchmark to measure the performance of other algorithms to find out which algorithm performance is closer to shortage job first. So it is used in benchmark analysis, benchmark performance comparison. I can compare the performance of other practically implementable scheduling techniques with respect to shortage job first by way of writing a C, C++, Java or Python program for SJF and other algorithms to find out which algorithm's performance is closer to shortage job first. So that is reason number one for having shortage job first in the literature for making benchmark performance analysis. Number two, what is the other reason for having SJF? Yes, of course, we cannot implement SJF with real burst times or known burst times, but however, we can implement it with what is called predicted burst times. Prediction. Like for example, these processes came at time t without running on CPU. We can anticipate, we can predict, we can guess how much time P1 may take, P2 may take, P3 may take, P4 may take. We can have some techniques like based on the size of process you can predict. How, sir? How do we predict based on the size? Suppose imagine, for example, a process Pi has come out of size 100 KB. Then I would go into the history to find out, have we completed a process of similar size, 100 KB? If I find that maybe in earlier occasion, I have completed a process of 105 KB, 105. It took for 20 units, for example. So I can make an estimate that since my new process is almost of same size, so maybe this process also may take 18 to 19, 19 to 20 units. Prediction based on size. If not, prediction based on type. We categorize the processes, OS process, interactive, foreground, background, and then we can have a range for each of these categories and type. so that whenever a new process arrives, we find out what is its type or category, and we can take the burst time from the given range, lower bound and upper bound, some values. So these are some static techniques, but we also have some dynamic techniques, predicting the next CPU burst based on some concepts like machine learning, regression analysis. That means we will see on previous completions and previous predictions. Based on that, we can anticipate, we can guess the next prediction. And that approach, that algorithm is called exponential averaging technique. So the most prominent technique for estimating the next CPU burst of the process is called exponential averaging technique. So what is exponential averaging technique? Let's try to understand it from here. But before that, I will go back to the same points which I gave in my first slide. So remember, shortest job first is an optimal algorithm for the reason I told. It gives minimum average waiting time for a given set of processes. Okay, these two we'll see. So how do we determine the length of next CPU burst? So we have estimate. So we are going to estimate it. We are going to estimate the next CPU burst. So how do we estimate? So here is the answer for estimation. Determining the length of next CPU burst. So I would like to, boys and girls, first explain to you what is the idea of next CPU burst by means of a simple diagram, so that you can understand well what is the meaning of next CPU burst. So boys and girls, please have a close look at this. So imagine, for example, this is my process. All right, this is my process, and this is the life cycle of the process. This is the life cycle of the process I, and I will divide this into two parts. All right, so check here. So this arrival time of the process, it arrives in the ready queue. This waiting time is, we have already said, it's called waiting time in ready queue. And then perhaps it got its chance to run on CPU. Okay, this is the first burst, BT1. After that, it went for IO operation on some IO device. So this time it spent is called IO burst time. Completing IO, the process will come back to ready queue, right? And it wait another time, and then it runs on CPU for some time, another burst, BT2. And then it got preempted here. So when it get preempted, it come back into ready queue, awaiting to this another waiting 3. Now, boys and girls, at this point of time, I am to tell you that at this point of time T, the process is waiting in the ready queue perhaps to get a chance to run on CPU again. So while waiting in ready queue, we want to estimate how much next CPU burst, next time when it is going to run on CPU, how much amount of time it is going to run for. That is called the length of the next CPU burst. Length of my next CPU burst. So essentially you should see that the process has already completed two bursts, burst 1 and burst 2. If I call the completed burst time as T1 and this is T2. So in general, Ti is completed burst time, and predicted burst time we will indicate it by a symbol called tau. Tau is used for prediction. So boys and girls, if you look at this framework here, essentially you can understand this ideology. Can only estimate the length, should be similar to the previous one, then pick process with shortest next CPU burst, right? Can be done by using the length of previous burst using exponential averaging. So the idea is like this. Let T an actual length of nth CPU burst, T1, T2, T3. Tau n plus 1 is the predicted value of the next CPU burst. So next CPU burst is indicated by tau n plus 1. There is some alpha constant lying between 0 and 1. So the formula for exponential averaging technique for predicting the next CPU burst is given by this. The formula, I repeat, the formula for predicting the next CPU burst of the process, or length of next CPU burst of the process, as per exponential averaging regression machine learning model regression technique, is tau n plus 1 is equal to alpha Tn plus 1 minus alpha tau n. So if you look at this equation, boys and girls, if you look at this equation, the next CPU burst prediction is based on previous completed and previous predicted. How much weightage we are giving to both is controlled by the value of alpha. If alpha is equal to half, then you are giving 50% weightage. If you take alpha is equal to 0.7, 70% weightage here, 30% weightage here. So essentially, in predicting the next length of the next CPU burst, I am giving weightage to previous completed and previous predicted. And moreover, if you observe this equation mathematically, from the mathematical perspective, this is looking like a recurrence. Tau is computed again in terms of tau, right? That is called recurrence. So how do you solve this? Solving this recurrence, basically, maybe I will show it here. How do you solve the recurrences? Tau n plus 1 is equal to alpha Tn. I'm trying to tell you why is it called exponential averaging, 1 minus alpha tau n, equation 1. If you find the value of tau n from right hand side, it will be alpha Tn minus 1 plus 1 minus alpha tau n minus 1. Is it not? Equation 2. If I have n plus 1, I have n. If I have n here, it will be n minus 1. If you substitute this value back in equation 1, this is called back substitution, and rewrite tau n plus 1 next CPU burst. Okay, so that will be alpha Tn plus 1 minus alpha into this value, alpha Tn minus 1 plus 1 minus alpha tau n minus 1. On expansion, it will become alpha Tn plus alpha into 1 minus alpha Tn minus 1 plus 1 minus alpha square tau n minus 1, equation 3. Next time you expand 1 minus alpha cube tau n minus 2, like that it keeps on working until it reduces down to tau 1. Tau 1 will be called the initial guess. Tau 1 will be called the initial guess. When the process comes into the ready queue for the first time, I am going to guess this value. This will be called as the base condition of the recurrence. Every recurrence, you know, should have base condition. So this, given the value of the alpha tau 1 base condition, given the value of alpha, you can always estimate the next CPU burst. Okay, this is a correlation trying to show between the correlation between the next CPU burst and the guess tau I. So this is the actual burst and this is the tau I. You can see the correlation. Okay, there is a correlation. This is tau I. The blue ink is tau I, and this is Ti. This is Ti. Look at this, Ti and tau I comparison. So almost it is in correlation, we can say, to the actual burst time. So same expansion is given here. Alpha equal to 0, then it will become tau n. That should not happen, and alpha equal to 1, it will depend on the previous completed burst if not. So this is expansion which I said just now. So you go up to tau 1 or you say tau naught, nothing, both will be same basically. So that's why it is called exponential averaging technique. Okay, and we have a variation of shortest job first, boys and girls. We have the variation of shortest job first, and that variation is called preemptive version of shortest job first, popularly known as shortest remaining time first. So how do shortest job first works in preemptive mode? So let's try to analyze it here. Okay, so let's try to analyze. Preemptive version of shortest job first called SRTN. So in short, generally we write SRTN, shortest remaining time first, preemptive version of shortest job next or shortest job first. So point is, whenever a new process arrives in the ready queue, the decision on which process to schedule next is redone by using the shortest job first algorithm. Whether are we going to continue to running process, or are we going to give the chance to the new process? So is SRT more optimal than SJF in terms of the minimum average waiting time for a given set of process? We have to analyze that. So this is a question that we have to address, but let me tell you the working principle of shortest remaining time first, also called preemptive SJF, is preemption of running process. Preemption of running process. Is based on the arrival or availability of a strictly shorter process. Preemption of the running process. When are we going to preempt? Preemption of the running process will be based on the arrival or availability of a strictly shorter process. Mean, first step is, among the processes present, we are going to start with the process having the least burst time, like SJF. But we are not going to run till completion. We are going to run the schedule job, dispatch job, right, until a new process comes. When a new process comes, we compare what is the burst time of the new process and what is the remaining burst time of the running process. If the burst time of new process is strictly lesser than the remaining time of the running process, then preempt the running process and give the chance to new, because this is preemptive algorithm. Preemption is based on the availability or arrival of a strictly shorter process. Strictly shorter process. So that's the logic behind SRTF. Otherwise, we continue the running process like SJF. Okay. In case if all the arrival times are same, then SRTF and SJF both will be working out to be same. Please understand that. If all arrival times are 0, then there will not be any difference between SJF and SRTF. When arrival times are different, then only we'll have the difference between SJF and SRTF. To analyze that, we will take a simple example. So boys and girls, please have a look at this data set first. Then I will give my own data set also. At time 0, we have only P1, so we are going to start with P1. But we are not going to run P1 till completion. P1 is going to run till time 1. This is 0 till 1. At time 1, remaining time of P1 is 7. And the new process P2 is having a burst time of 4. 4 is less than 7, so we preempt P1 and give the chance to P2. P2 is going to look at that. P2 is logically first going to run till time 2. But at time 2, new process P3 is having burst time 9 and this is 3. So no preemption. So we continue P2 till 3. At time 3, P4 comes. So it has run for 2 units. Its balance is 2. New process is shorter. No, new process. So new process is not shorter. Then in that case, what are we going to do? We are going to run for all 2 units. So therefore, P2 is starting from 1 and completing at time 5. 1 plus 4. Now at that point of time, processes that are available are P4, P3 and P1. Among them, anyway this is over, right? So among them, P4 is having the least burst time. P4 needs 5 units, so therefore it is going to complete at 10. And thereafter, P1 is having lesser burst time 7, so it is going to complete at 17. Because no new process is come, no preemption. And lastly, we are going to complete P3 needing 9 units, so means 26. So if you compute the average waiting time, P1 has waited for, you can see, came at time 0, it got scheduled at 10, so 10 minus P1. P1 came at time 0 and got scheduled only at time 10 or 9. So it should be like, here P1 has run, right? P1 has run initially 1. So from 1 to 10 it has waited. So therefore waiting time is 9. P2 got scheduled at time 1 and finished. It has not waited anything. So 1 minus 1, 0. P3 waited how long? Look at this. P3 came at time 2 and got scheduled at 17. So 17 minus 2. That is the waiting time. And lastly, P4 waiting time is 5 minus 3. So that's the approach. 26 by 4, 6.5 is the waiting time of this. You can compare the waiting time with shortest job first. We'll calculate, we'll work out as a matter of comparison. We'll see what is going to happen if I go for shortest job first, non-preemptive version of shortest job first. So here we are going to draw that chart for non-preemptive SJF. So this is SJF. This is SJF, non-preemptive. Is it not? Non-preemptive. So what is going to happen? How will the scheduling be done? Please observe CPU. Time 0, we have P1. So I will take the original data set. We have P1. Non-preemptive. So there is no chance we complete P1 at time 8. After that, we'll take up P2. Need 4 units. So complete at time 12. After that, we take up P4. P4 need 5 units. Complete at time 17. And then finally P3 need 9 units, 17 plus 9, 26. So if you now compute the average waiting time, boys and girls, if you compute the average waiting time using shortest job first. So P1 has not waited anything 0. P2 has waited for 8. P2 came at time 1 and got scheduled at 8. So 7. P3 came at time 2, got scheduled at 17. So waited for 15 units. And P4 came at time 3 and got scheduled at time 12. So it waited for time 9 units. So boys and girls, this is my average waiting time. 22 plus 9, or maybe you can calculate, yeah, 22 plus 9, 31. 31 by 4. So which happens to be 7.75 you can see. 7.5 rather, 7.7. Okay, so that is greater than 6.5. So therefore, I can say in terms of performance, SRTF is better than SJF in terms of average waiting time. Is it not? In terms of average waiting time, SRTF is better than SJF because its waiting time is 6.5 and that waiting time is 7.75. So naturally, SRTF is better than SJF. So question was asked: is SRTF more optimal than SJF in terms of minimum average waiting time? Yes, sir, it is better. That is what we are trying to finally answer it. Maybe perhaps I can take one more data set for you as a matter of practice to work out SRTF. Okay, so let's say this is my data set, process number, arrival time and burst time. How do SRTF work? Boys and girls, I am to tell you that in earlier papers of GATE, lot of problems, lot of questions were asked based on SRTF. In earlier papers of GATE, lot of questions were asked in SRTF. So essentially, I wanted to say that this is a very, very important algorithm, very important algorithm. 0, I would take it as 7, and 1, I would take it as 5. At time 2, I would take it as 3. At time 4, I would take it as 1, something like this. So how do we get the Gantt chart? How do we prepare the Gantt chart using SRTF? So ideally speaking, you should pause the video and then essentially prepare the Gantt chart, and then you can compare with my answer. You should do like that. Okay, you should be doing like pause the video, prepare the Gantt chart, and then you can compare with my answer. That is the correct approach. So let's start. SRTF. So I am simulating for SRTF. Time 0. We are going to start with P1. P1 is going to run till 1 unit. Its balance is 6, new process is 5, preempt in favor of P2. P2 is going to run for 1 unit, new process arrives at time 2. P3 with time burst time of 3 units, new process is shorter, preempt in favor of P3. So you mark the remaining time, this is 6, now this is 4. Now P3 is going to run till 3, essentially 3. Now sorry, 3 there is no process. So essentially it is going to run till new process 4. Now its balance is 1, its balance is 1, new this process is also 1. So when burst times are same, we are not going to preempt, we are going to run and complete the process. When burst times are equal, there is no preemption. So preemption will happen only with strictly shorter process. Preemption will happen with only strictly shorter process. So it will continue. It will continue and complete. So P3 is over, and then followed by that P4 will take the charge because that is the least process. So it completes at time 6. Then after that P2 is the next lower with 4 units, complete at time 10, 6 plus 4, and finally P1 will take 6 units, complete at time 16. So boys and girls, this is the Gantt chart using SRTF. So that's the algorithms of shortest of first and shortest remaining time first. So in the next session, next video, we'll look into other scheduling techniques like priority based scheduling and round robin. Okay, till then, take care. Thank you.